Participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star 1 on your phone to ask a question. I would like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to Mr. Steve Cole. Thank you. You may begin.
Okay, thank you, and welcome everyone to this NASA media briefing on new science results from the Hubble Space Telescope. Jupiter's icy moon Europa was the target of a unique Hubble observation campaign investigating the existence of a subsurface ocean on Europa. And a spoiler alert, despite what some media have reported recently, this finding has nothing to do with detecting life on Europa. The new research will be published this week in the Astrophysical Journal. We have 4 participants today for the call. First will be Paul Hertz, Director of the Astrophysics Division in the Science Mission Directorate here at NASA headquarters in Washington. William Sparks, who is the lead author of the study, an astronomer with the Space Telescope Science Institute in Baltimore. Brittany Schmidt, Assistant Professor at the Georgia Institute of Technology School of Earth and Atmospheric Sciences in Atlanta. And Jennifer Weissman, Senior Hubble Project Scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Our speakers have a number of images to present during their presentations. We have a link you can go to follow along there. That link, please go to nasa.gov/live, that's L-I-V-E. That has information about the results and a link there to the briefing graphics. All right, well, we'll begin with Paul.
Thanks very much, Steve. The science results that we are announcing today are based on observations of Jupiter's moon Europa made with NASA's Hubble Space Telescope. The Hubble Space Telescope is shown in Figure 1. Europa is a world of great interest. NASA is working on a mission to study Europa up close. But we're impatient and we want to study Europa now. And we cannot fly a mission up close. The next best thing is to use the Hubble Space Telescope and some of its unique capabilities to study Europa from afar. Hubble is a powerful observational tool. Whether we are studying the most distant galaxies in the universe or worlds like Europa right next door in our own solar system. Earlier this year, NASA conducted a senior review of the Hubble Space Telescope along with our other astrophysics missions to review its science productivity and efficiency. Not surprisingly, Hubble was rated very highly and passed the review with flying colors. NASA plans to keep Hubble operating as long as it's scientifically productive. And as today's results demonstrate, we believe that will be for years to come. And we hope that Hubble will be operating in the years after we launch the James Webb. We hope that Hubble will be operating in the years after we launch the James Webb Space Telescope to provide complementary science capabilities. So, for today's science results from the Hubble Space Telescope, I'm going to pass it off to William Sparks.
Thank you. So, Figure 2. Today, we are presenting new Hubble evidence for water vapor plumes being expelled from the ice surface of Europa. Europa is the second closest Galilean satellite to Jupiter, a classical icy world and a truly compelling astrobiological target in the solar system. Observations indicate a global, saline, liquid water ocean engulfs the moon at the present time, hidden under miles of ice. If there are plumes emerging from Europa, it is significant because it means we may be able to explore that ocean of Europa, for organic chemicals or even signs of life without having to drill through unknown miles of ice. We made the findings by using transit imaging observations, which I'll explain in a moment, observing the silhouette of Europa against the bright background of Jupiter, and looking in ultraviolet light for signs of plumes coming from the surface of Europa. This idea came from exoplanet atmosphere studies. As an exoplanet, that is a planet orbiting a star other than the Sun, passes in front of its host star, some of the light of the star passes through the atmosphere of the planet and is influenced by it, so we can infer what the properties of the exoplanet atmosphere are. Here, we're taking images, but the principle is similar. The figure shows a Hubble ultraviolet transit image with the Galileo spacecraft map of Europa superimposed. The features we're talking about, the plume candidates, can be seen around the southern region towards the bottom of the figure, offset from the edge of Europa. The image is shown in such a way that any regions where absorption may be occurring appear bright. As you can see, there are intriguing features apparently emerging from Europa, though I do want to inject a word of caution. We are really working at the limits of Hubble's unique capabilities. Figure 3. Previously, in 2012, a team led by Lorenz Roth found evidence of plumes from Europa also using Hubble. They obtained spectroscopic images that showed the dissociation products of water, namely hydrogen and oxygen, in emission. Their 2012 hydrogen image is shown on the right of the figure. On the left is a raw transit image from our program of 2014. The dark disk in the center is Europa, and the bright background all around is Jupiter, behind Europa. To the left-hand side, Europa is darker, that's the trailing hemisphere, and on the right is the leading hemisphere with the north pole of Europa towards the top. The image shows dark fingers or patches of possible absorption in basically the same place that Roth and his team saw off-limb auroral emission, although we're at a slightly different longitude. Next figure, figure 4. This is an animation to show the general idea of plumes. If water vents open in the ice, then plumes may emerge and rain back down onto the surface. If they do, then it may be a lot easier to access material that was once in the ocean of Europa. Next figure is figure 5. Europa orbits Jupiter every 3.5 days, and on every orbit it passes in front of Jupiter, raising the possibility of plumes being seen as silhouettes absorbing the background light of Jupiter. Europa is tidally locked to Jupiter, and so always presents the same viewpoint. We always see the same side of Europa as it moves from left to right in this illustration. Figure 6. This is an animated GIF illustration of a transit. There is some complexity in the transit as Europa crosses in front of Jupiter, while Jupiter moves and rotates behind Europa. This particular image is in the near ultraviolet. The observations we've been talking about today were taken in the far ultraviolet, where the appearance of Jupiter is smoother, lacking in contrast, and the ice of Europa is very dark. The next slide. We obtained 10 images of Europa as it passed in front of Jupiter, and statistically significant evidence for off-limb features, possibly plumes, was found on 3 occasions. This figure shows those 3 images with a color scale that relates to the likelihood the features are real. The Galileo spacecraft image of Europa has been inserted for illustration, showing again that we always see Europa from the same perspective. This is significant because it means that if the features are real, they have to be intermittent, because we're always viewing the same part of Europa and we did not see anything on 7 occasions. The possible plumes are mostly clustered around the southern edge, although there is also one candidate at a more equatorial location, which you can see in the central image from March 17th of 2014. The next slide, figure 8. In conclusion, this slide repeats the image of the first plume candidates. If plumes exist, this is an exciting finding, as it potentially gives easier access to the ocean below and would allow us to search for signs of life in the ocean of Europa without needing to drill through miles of ice. However, I do want to stress that the observations are at the limit of what Hubble can do. We're not aware of any instrumental artifacts that could cause these features. They are statistically significant, but we remain cautious because we are working at difficult wavelengths for Hubble. We do not claim to have proven the existence of plumes, but rather to have contributed evidence that such activity may be present. Thank you. The next person to speak will be Brittany Schmidt.
Yes, hi everyone. So I'll be talking to you a little bit about the geologic context of Europa and comparing it to Enceladus, the only known object where we have water ice plumes. Those were verified by the Cassini spacecraft. So let's go ahead and take a look at figure 9A and figure 9B. In 9A, I'm showing Europa in cross-section to give you a sense of how Europa is built. So it's got an ice shell on top of a liquid water ocean with an interior made of silicates and an iron core. Europa was mapped and measured by the Galileo spacecraft to give us this data. It's a little bit different from Enceladus, which is the picture in 9B. Europa is about the size of the Earth's moon, about 1,500 kilometers in radius, whereas Enceladus is about 250 kilometers in radius. It's known that Enceladus has a south polar sea, and Cassini detected the south polar jets that are shown in this figure. A global ocean is possible on Enceladus, but has not yet been confirmed. In figure 9C is an image from Cassini showing the geology of Enceladus. Enceladus can be thought of as having kind of two geologic patterns. One is confined to the south polar region and one other area where fractures, at least in the South Pole, are sourcing material from deeper below. And the remainder of the surface is heavily cratered. And so it's kind of got this more simple geology, at least than when we look at Europa. If you go to figure 9D, I'm showing an image of chaos terrains on Europa from Galileo. What you're seeing is a complex feature where ice rafts have broken apart and new material has been produced in between those ice rafts. So that's a chaos terrain, and in figure 9E, I'm showing a close-up picture from Galileo as well of ridges crossing the surface of Europa. If you look at Europa in high resolution, it's covered with ridges and fractures, much like a tectonic yarn ball. And so when you see these images, the obvious feature in the middle is what we'd call a classic double ridge. So this is just to point out that whereas on Enceladus, the geology makes it a little bit obvious where the activity has been, on Europa there's activity everywhere, which both could lead to plumes or could muddy the interpretation. So now we're going to discuss really quickly how this might work. In figure 10A, I'm showing an artist's rendition of possible delivery of water to the surface of Europa. And then in figure 10B, a figure from Fagins et al., 2003, who just gave a summary of possible mechanisms for how to get water near the surface of Europa. It turns out that tidal activity of Europa should power lots of stresses and strains to its surface, but it's very difficult for those tides to actually break through as much ice as we think is present on Europa. And so this relatively simple drawing is somewhat difficult to understand in the context of Europa's geology, but nonetheless, it's a possible scenario for bringing water near the surface. In figure 11A and 11B, these are alternative scenarios. In 11A is an artist's rendition of chaos terrain formation from a paper by myself and my colleagues. And the figure below that is a figure showing kind of how that proposed mechanism for getting water near Europa's surface might work. And the point for showing these two models, both in figure 10 and figure 11, along with the surface geology of Europa, is just to say that there are a lot of ways that we think water may reach near the surface. It may not come directly from the ocean, but most of the material in the ice shell and that might be expressed near the surface spent some time near the ocean of Europa. So these are the kinds of questions that we'll be looking to answer and determine the differences between these scenarios with future exploration. I'm going to go ahead and pass this on now to Jennifer.
Thank you. I want to say a little more about the Hubble Space Telescope. Its very clever uses of the unique capabilities of the Hubble Space Telescope that have enabled this detection of evidence for water plumes on Europa. Hubble is the only telescope right now that we have that's capable of observing Jupiter and Europa to this level of detail in ultraviolet light. The research team has used these ultraviolet capabilities of an instrument on Hubble, the Space Telescope Imaging Spectrograph, or STIS, to detect these plumes or evidence of plumes as Europa transited in front of Jupiter, which provides a smooth background in ultraviolet light. As was mentioned before, previous evidence for water plumes was also found in ultraviolet light with Hubble, also using the STIS instrument, but using it in a different way to detect components of water vapor outside the ice cover of Europa. Now, we're thrilled about these findings because this is enabled by the fact that the STIS instrument was repaired by astronauts back in 2009 on servicing Mission 4. So because of that heroic repair, we are achieving tremendous science advances and discoveries like this. And in fact, we're making a special effort now to use Hubble's unique ultraviolet observational capabilities while we still have them by encouraging scientists around the world to propose top science where ultraviolet light is needed, such as these observations of Europa. In fact, the Jupiter system is recently in the news because we recently used the Hubble STIS instrument to observe the bright ultraviolet aurorae on Jupiter, just as the Juno probe was entering Jupiter's orbit to study its related magnetic fields. So this is a great example of how NASA missions support one another. These new Hubble observations of Europa, as well as previous ones, are helping to build on earlier imaging of Europa from the Galileo and Voyager missions, and is helping to inform the planning of future missions to explore Jupiter and its moons. Now, we're particularly excited about using the James Webb Space Telescope, which you can see in Figure 13. By the way, Figure 12 shows an image of astronauts repairing that STIS instrument on Hubble in 2009. Figure 13 shows a schematic of the James Webb Space Telescope, which launches in 2018. And we're excited because we plan to use the James Webb Space Telescope to look for additional evidence of Europa water using infrared wavelengths of light. So with that, I will pass it back to Paul Hertz, who may have some additional comments.
Thank you, Jennifer. For a long time, humanity's been wondering whether there is life beyond Earth. And we're lucky to live in an era where we can address questions like that scientifically using all the tools available to us, including the Hubble Space Telescope. On Earth, life is found wherever there is energy, water, and nutrients. So we have a special interest in any place that might possess those characteristics. And Europa might be such a place. Today's results increase our confidence that water and other materials from Europa's ocean, Europa's hidden ocean, hidden under miles of ice, might be on the surface of Europa and available for us to study without landing and digging through those unknown miles of ice. And with that, I'll hand it back over to our moderator, Steve.
Okay, thank you. And now we will take some questions from the phone lines. Operator, if you could remind folks how to ask a question.
Absolutely. If you would like to ask a question at this time, please press star 1, unmute your phone, and record your name clearly. If you need to withdraw your question, press star 2. Again, to ask a question, please press star 1. One moment, please, for the first question.
Okay, our first question will come from Peter King at CBS News. Go ahead, Peter.
Thank you very much. You hearing me okay?
Yes.
All right. I have a feeling that somewhere there are some shuttle astronauts or former shuttle astronauts who are smiling right now with this news. And I'm not sure who this question should go to, but you say that Hubble has now been stretched to the limit. It's a two-part question. First of all, do you keep studying this with Hubble? And part two is, how much further will the capabilities of the James Webb Telescope allow you to find out more about this phenomenon?
Jennifer, you want me to take that?
I can. Well, let me just say quickly that, of course, we want to keep using the Hubble Space Telescope to study Europa and its environs. So we'll continue to be using it the best we can to study, to look for things like plume activity. Remember, it looks as though the plume activity, if it is there, is variable. So sometimes we see it and sometimes not. So that presents its own interesting challenge. But we are going to continue to use Hubble the best we can to see evidence of water and plumes. And, of course, the James Webb Space Telescope will give us access to other transitions of water molecules that can be seen in infrared light. So we'll certainly be exploring those new avenues of evidence as well. But I'll pass it to Paul to add any thoughts on that.
No, that was a complete answer. Thank you.
Okay, our next question is from Alex Whitsey at Nature Magazine. Alex?
Yes, hi. I also had questions about timing. First, Bill, if these observations were taken in 2014, why are you only reporting them now? And then if someone can specifically address whether there have been scheduled Hubble observations looking for plumes since the 2014 cycle, and whether there are any upcoming in the next months or years. I'd like to know if there's specific proposals that have been granted time.
I can take a stab at that, yes. The question is, why did it take so long? It's a rather complicated way of observing to make these observations. We take the observations in what's called time tag mode, where we record the arrival of every photon in the image with a position and a time of arrival. And then we reconstruct the image from a table of events that has about 50 million events in it. There was a lot of software development that was necessary to optimize the processing of those images, and we wanted to be as careful as possible with the analysis and develop models of the scene, Europa and Jupiter both together, and to carefully analyze the relative motions of Europa and Jupiter together. And after we'd done all of that and we started to get our results, then we had to think about what it meant, whether we'd done the statistics right, and check this and check that and get the paper written. And it takes a while to get these things. It's not just taking a picture. It's a much more complicated process for the data analysis. Subsequently, subsequent to this paper being submitted, we did observe 2 more transits, and we've just started analyzing those data, and we'll certainly be reporting on that as soon as we have the information from them. Was there anything else?
No, I think that covers it. Thank you. Our next question is from Irene Klotz at Reuters. Irene?
Hi there. Thanks very much. I wanted to know if the Europa mission currently in the planning stages could make use of this as far as like a timing of a mission or even doing what Cassini's done at Enceladus to sample any materials in the plumes.
Okay, we have here Kurt Niebuhr, who's the Europa program scientist at NASA headquarters, who's going to take that question for you, Irene.
Thanks, Amy. I think one of the biggest unknowns we have with these putative plumes is understanding their timing. And I think the more observations we can get with Hubble and with JWST to better understand that, the better we can use that to construct a schedule for when we search for these plumes at close range from the Europa flyby mission.
Okay, thank you. Our next question comes from Maddie Stone at Gizmodo.
Hi, thanks for taking my question. The first part was going to be about the future mission to Europa, but since we just answered that, I was also interested in hearing whether the Juno spacecraft might be able to shed any more light on activity on the surface of Europa.
The Juno spacecraft does have a powerful suite of instruments, but the mission is focused on Jupiter, and we took great pains to make sure that spacecraft does not get anywhere near Europa because we want to protect Europa from contamination. So the Juno spacecraft isn't slated to take any observations of the Europa or the European environment during its mission.
Okay, thank you. Our next question is from Kelly Beatty, Sky and Telescope. Kelly?
Yeah, thank you. I was wondering if you could make any kind of estimate of the mass of the water vapor that's being ejected during these, and if you anticipate that it's more than water vapor, might there be some kind of component in the torus of gas around Europa in its orbit that can be detected?
I guess I should take that. This is Bill. Getting the quantitative amount of material that would be required to produce absorption at the level we see is quite difficult. We only have broadband imaging observations. We don't have the spectroscopic diagnostics that the previous team had. But that brings with it some advantages and some disadvantages. So there are several options. We could be seeing absorption from water vapor itself, or from the products, the dissociated water, oxygen primarily, or from small ice particles. The plumes of Enceladus have an ingredient of micron-sized ice particles. All of those can cause absorption. They're roughly speaking of comparable levels. And so when we do that, we also have to make some instrumental corrections, which are very uncertain. But we come out with numbers that are in the range of million kilograms or a few million kilograms. And that's not too far off what the previous team inferred for their plume models. In terms of the plasma torus beyond Europa, we're only looking very close to the limb. The features that we've measured and see are quite localized, and I don't think we would have any sensitivity to anything beyond that.
Okay, thank you. Our next question is from Eric Berger at Ars Technica.
Hi, thank you very much for doing this. I was hoping maybe we could maybe explain one of the mechanisms by which you think that this water vapor might be reaching the surface. And if so, if you had some CubeSats on the flyby mission, I mean, could you drop them down in one of these plumes when they were venting and get some information, or maybe even get some information about the surface activity? Thank you.
Well, I can address the CubeSat suggestion you made. We did actually examine various options for additional deployable probes we could put on the Europa flyby mission, and in the end, we decided that the science value of them was not worth the risk. We have 9 instruments on the Europa flyby mission. Each one of those instruments is a very powerful plume hunter, in addition to its primary science investigation. So with those 9 instruments, we feel we already have the ability to aggressively investigate these plumes.
Okay.
And if you'd like, I could comment on.
Please go ahead. Please go ahead.
Sorry about that. Yeah. So the figures that this is Brittany Schmidt. The figures that I showed of 2 examples of Europa's geology and 2 examples of models for water making it to the surface. Those are really supposed to just point out that there's a wide range of hypotheses for water on Europa and for how that would actually ascend. So hopefully those kind of bracket the ends. One is the kind of very simple model. One is a very specific model for one specific type of terrain. But that's the reason we explore, and we've got lots of hypotheses to look into with future missions.
All right, our next question is from Tracy Watson at USA Today.
Hi, thanks for taking my call. I'm wondering if you could help me put your announcement into context. How much uncertainty was left by the spectroscopic data from HST? And you emphasized the uncertainty of this finding. How much more certain does it make it that you have seen the plumes? I'm not looking so much for exact quantitative answers. It's just kind of getting a sense of how much confirmation this provides. Thanks.
It's a good question. The so-called statistical significance of these results is basically the same as the previous result. How much? So in a formal sense, the probabilities, the chances of this occurring, if it's just due to random noise, are very low. And so in the formal sense, we have what we call a statistically significant result. But the problem is that there may be something we don't understand about the instrument or about our model of the scene or what Europa looks like in the ultraviolet light. And so it's more of a subjective uncertainty than a quantitative uncertainty that when you make an observation at a wavelength that's really challenging Hubble, so we're in the very far ultraviolet here, there may be things about the instrument and the telescope that we currently don't understand, although we've certainly explored all the things that we do understand, and we are not able to find any artifacts that can produce these things. But there's always the possibility that we haven't understood everything, and so we want to be a little bit cautious. There are a couple of other reasons as well. The intermittency can be interpreted as a pro and a con. The fact that we don't always see them, that's both an advantage and a disadvantage. But basically, it's just a slight worry that we don't understand everything about a challenging wavelength at which we're working.
All right, our next question is from Mark Carreau at Aviation Week.
Yes, regarding the future mission to Europa, what sort of spectroscopy have you signed up for, or could you possibly add to assess this vapor for organics or whatever else interesting might be present? Thank you.
Yeah, this is Kurt Neighbor. For the instruments we have on the Europa mission, they really span the wavelength range from ultraviolet, which is what we're talking about today, through visible, which is what your eyes would see, and into the infrared, which is the same region that JWST looks in. Going beyond that, they also see in the thermal range, which is heat vision. So they could actually see the hot spots on the surface, the vents themselves, that are going to be much warmer than the surrounding ice. And this is where the plumes would actually originate from. So that's the kind of imaging or spectroscopy we would have. Beyond that, we also have compositional instruments that, should we be able to fly through these plumes, like Cassini does at Enceladus, and that would certainly be a high priority for the Europa mission, we could use these compositional instruments to actually ingest samples of the plume material and analyze them in these instruments. And doing that, we can get an idea of what materials are inside the plumes and inside the dust and the ice particles. And when we've done that at Enceladus, it has revealed a tremendous amount of information about the ocean that is present beneath Enceladus's ice shell, and we would kill to have that kind of information and data for Europa.
Our next question is from Bill Harwood, CBS News.
Thanks. I'm trying to quickly think of something to do with that last line about killing for data, but no, I'm just kidding. A real quick question, and I may have missed this, and I'm confusing myself maybe, but if they're not water vapor plumes that originate from this presumed subsurface ocean, what other natural phenomenon could explain the readings? And I think you touched on that, but I may be confused myself. I'm trying to understand what other explanations there are if these are not water plumes. Thanks.
Perhaps I should take that. I'm not aware of any other plausible natural explanation for the appearance of these patches of absorption. The only other possible explanation that we've been considering is the possibility of some internal instrumental effect. We've obviously checked for those that we know about and haven't found any, but basically that's in our minds that's the alternative. They appear to be real. The statistical significance is pretty good, and I don't know of any other natural alternative.
Our next question comes from Leo Enright, Irish TV.
Thanks very much for doing this. It took me a couple of minutes to understand how this work advances what Lorenz Roth and his team did several years ago. But if I just could try and clarify in my own mind what it is. Basically, you're saying that you detected, you believe, this plume in January, then on St. Patrick's Day in March, and then in April of 2014. You also say that you saw nothing on 7 occasions. Now, if I remember rightly, Roth said he saw nothing in January, where you say you saw something, in February, November, and December of 2014. So I'm trying to just understand how is this the point that you actually see a sequence? And secondly, if I may add a completely different question, is there a prospect at some stage during these Hubble observations of getting some stellar occultation that might allow more fine-grained analysis, or is that just not written in the stars?
Yes, you're right that we have upper limits and we have images in which we have evidence of features. Roth have only ever seen anything once, and they tried to follow it up subsequently, including, as you noticed, observation, which we talk about in the paper, within a relatively short period of time of our observations. We're not proposing a sequence. We're not proposing any models. All we're saying is that if they're real, they have to be intermittent. Roth explored a particular model, which was a tidally modulated model, the same as Enceladus. We didn't try to constrain our observations in any way, and we came up with the results that we've presented today. It's significant because previously there's just been one piece of evidence that these things exist. Now we've got a couple more pieces of evidence that they exist. On the occultation, I would pass that over to someone else.
Does anybody want to take that question? Okay. Well, then we'll move on to our next question from Alan Boyle at GeekWire.
Yes, hello. Thank you for taking the question. I wanted to ask, are these results really surprising? And if so, what did you find surprising? Thank you.
Bill, would you like to answer that?
I'm neutral on that. We knew we were sensitive to this. Our observing program was independent of Roth's. We proposed this before Roth made their announcement. We were configuring ourselves to detect this kind of thing if it was present. We didn't know whether it would be or it wouldn't be. There's no particular reason to suppose that plume activity would be particularly prevalent, but we know for a fact it occurs on Enceladus, and if it occurs on Enceladus, then why not on Europa? And as Brittany's talked about, there are mechanisms which could potentially drive cryovolcanism or water expulsion from the oceans, either directly or indirectly on Europa. So in that sense, it was one of the things that we'd written into the proposal that we would be sensitive to and we could find. Actually finding evidence, well, that's a different ball game, because then we really have to get into the details of what's significant and what's not.
If I could add to that, this is Brittany Schmidt. I just wanted to mention that the suggestion that material could be coming out of Europa was made during the Galileo era as well. Galileo, unfortunately, had suffered some issues with its antenna, and so was not able to send back as much data as it had hoped. But included in that was a single plume search, but they didn't find anything. We didn't really have the observing geometry to do that with the Galileo encounters and with the data limitations. So from a geologic or historical perspective, it wouldn't be so outrageous to expect these things to happen. I usually say to people that I'm not surprised, I'm excited and skeptical, right? So, but I think what Bill said is correct, that there's reasons to think it could happen, and good to see more ways of trying to get at that. But I wanted to make sure that it was noted that Galileo even had tried to do something along those lines.
Okay, thank you. Our next question is from Rebecca Boyle at New Scientist.
Hi, and I have no relation to the wonderful Alan Boyle. Thanks for doing this. Most of my questions have already been answered, but I wanted to ask about a couple things. First of all, of actually getting to this area with a Europa flyby mission, if it's in the South Pole, does that complicate matters for orbital planning? And also just wondering if you found what you found in this constituent-wise, and what's the limit of Hubble observation? Like, could you find anything beyond hydrogen and oxygen, any other volatiles that you might want to look for?
I'll take a stab at the beginning of that, if I may. The position isn't strictly the South Pole. There's a general tendency to be in that general area, but one of the candidates that we found was at a much more equatorial location. So I think we would need to do more work and convince ourselves of the location that was the most fruitful one to explore. And I'll let Kurt answer beyond that. In terms of the constituents of the plumes, I think Brittany alluded to this just a little bit, but we are not sensitive to the constituents of the plumes. Basically, anything that absorbs will appear in our image. We presume it to be water vapor or ice particles because that's what Europa is made of, and those molecules do absorb at the wavelengths we observed at, which is why we chose those wavelengths. The Roth team did have had spectral sensitivity, and they could sense hydrogen and oxygen. There may be other methods that could be brought to bear that would give us additional insights into that, but at the moment we do not really have that information, apart from knowing the fact that at these wavelengths water is what we would be most sensitive to.
Yeah, and if I could just add to that, this is Jennifer Wiseman. That's one of the reasons this new finding is so intriguing, is because it's a different technique that complements the Roth team. The Roth team used spectroscopy, so they really could discern evidence of dissociated water molecules, hydrogen and oxygen, The Sparks team discovered through imaging evidence of plume activity visually. So these are different approaches, but they complement one another, and they seem to both be independent evidence of plume activity on Europa. But Kurt Niebuhr, let me pass it over to you to answer the other part of her question.
Your question as to whether or not it would be difficult for us to get the spacecraft to an area near the South Pole. We are constantly adjusting our trajectory for where and how we fly by Europa, and we really covered it in quite a web of different flybys, and it's amazing to me the degree of flexibility we have. But we are intentionally constructing this mission such that if we find a feature like a plume or something else that we find interesting, that we can, within a week or two, adjust the trajectory so that we can potentially fly right over that. And with the instruments we have on board and the sensitivity, that gives us a lot. Because one of the papers Roth's paper about this said that we're looking at 5,000 to 7,000 kilograms per second of water mass being erupted, which is about an Olympic swimming pool every 8 minutes. But with the instruments we have on board, we are actually sensitive to about a kilogram or two per second of outgassing from the surface if we get close enough.
All right, our next question is from Jason Ryan at Spaceflight Insider.
Hey, thanks for doing this. I have a pretty simple question that may not have a definite answer. I noticed a lot of if, ands, or maybes when you were describing the plumes, and I was wondering if there's any idea of when we might actually have hard confirmation that these are plumes and what that would entail, that would require to happen. That's basically all that I got.
From my perspective, I would say there are two things that would help. One would be repeated Hubble observations and to continue to develop our understanding of the characteristics of this instrument. I think it is possible we could become pretty confident with just Hubble observations. The other thing that would really that could potentially nail it would be if somebody came in with a completely independent observing technique and the results were found to be consistent. There are lots of people are starting to think of lots of ideas about how one might look for plumes in ways other than with the STIS on Hubble. But so far, to my knowledge, no one has actually made a serious attempt to detect them.
All right, our next question is from Dave Mosier at Business Insider.
Hi, thank you for taking my call. I wanted to dig back into the ability of the Europa flyby mission to actually analyze these plumes. What are we looking for when we're looking for life there? Are we looking for a ratio of certain molecules? Are we looking for, a smoking gun kind of molecule? Maybe it's some form of carbon. Can you just get into that? And I know there's a project scientist in the room there, which I wasn't aware of, so maybe he could answer.
This is Kurt. There's 2 points I'll make. The first is to make sure that we're clear that the Europa flyby mission, which will launch in the 2020s, is not a life-finding mission. That mission is focused on assessing the habitability of Europa. And we do it in this way for a very simple reason. We know how to measure habitability. We have a lot of experience with that. We have a lot of instruments that are very robust and mature and good at doing that. When it comes to finding life, we don't have as much experience, and we actually have an ongoing and vigorous debate in the scientific community as to the best way of going about detecting life on a mission such as this. And we are encouraging that debate because that informs the kind of instruments we develop that we will eventually put on instruments to Mars and to Europa and to Enceladus that will actually actively look for extant life in those places.
All right, thank you, Kurt. Our next question is from Sean O'Kane at The Verge.
Hi, guys. Just really quick,
just wanted to know where this all fell in the timeline of sort of finding time on Hubble to make these observations. When did it all start? How long did it take to hear back? All that kind of stuff.
Our observations started at the end of December 13 and ran through the opposition cycle of 2014. Then we had a couple more observations the next year when Jupiter came around again in 2015 and again in 2016. The 2014 and 2015 timelines were dominated by observations in 2014 around opposition and soon after it. The 2016 observations we're still working on. So mostly it was post-opposition 2014, starting at the end of December 2013. Does that answer the question?
I think it does. Thank you, William.
I think it's also good to point out, this is Jennifer Wiseman, Hubble observation time is very competitive. So teams such as this would put proposals in to experts that are gathered by the Space Telescope Science Institute and NASA to evaluate them. And so this proposal was obviously ranked very highly by the science community as of being a very high science importance to be given time on Hubble. And I'm so glad because of these fantastic results.
All right, thank you. We'll be taking a couple of questions now from social media. If you have questions, please use the hashtag AskNASA. And once the call concludes in a few minutes, we'll be answering those on social media as well. But our first question, again, from Twitter, is from Twitter user SubOde, who asks, what are the chances of these plumes having life-supporting chemistry on Europa? Brittany, would you like to take that?
I would say the jury's out. We don't even know that on Enceladus yet. So it really depends on first whether these plumes are actually there. So that would be my comment.
If I could add to that just a little bit. Even if there is a small amount of biomass in the plumes as they start out from the ocean, by the time they get into space in the radiation environment of Europa at cryogenic temperatures, it's not going to survive. We'd have to be looking for the remains of something that was once protected in the ice or under the ice.
Okay, thank you. One more question. This comes from Facebook user Mike, who asks, what are Juno's capabilities? Can it analyze the water content?
This is Kurt. I think that's a good question. Juno is ideally built and suited for assessing the water content of Jupiter. And as I said, there's no plans to get any Europa data from that mission because its plate is already full. And the instruments aren't very well suited for Europa measurements.
Okay, our next follow-up question, actually, on the phone lines, will go back to Leo Enright from Irish TV.
Yeah, thanks very much. I was going to be a bore and chase up on stellar occultation, but I'll change tack and ask, you did show this image of Connemara chaos. So as an Irish journalist, I guess I have to ask, is there some suggestion that possibly, given your theories, one possible origin of these plumes could be, in fact, Connemara chaos?
I guess I should answer that. So the slides that I showed, this is Brittany Schmidt, are just the kind of end member scenarios, right? So we have static imaging and topography from the Galileo mission of Europa, and there's been a whole slew of models of ridge formation, of impact cratering, and of the formation of chaos terrains that would suggest various amounts of water. The most recent of which was our paper in 2011, which actually suggested that Connemara chaos could be quiescent while others might be more active. But that's the kind of thing that has to go back and be confirmed. So as I mentioned, there's a wide range of people who've worked on this problem. Those are kind of two end-member sets that go well with the kind of charismatic geology of Europa, of which Connemara chaos is perhaps the best known. There's certainly the possibility that would be a mechanism for bringing water near the surface, such that it, could work out. Plenty of reasons why that might not be expected as well. So I would say the jury is out on that one, and looking forward to confirming it, or in all actuality, probably finding out we're all wrong and something else is happening when we get there.
Okay, thank you. And that's all the time we have for questions during this call. Journalists who might want to follow up on other questions, please contact the NASA communications staff, and we can work with you to set up interviews. And if you're listening online, we will be taking questions via social media with the hashtag AskNASA for the next hour or so. We have a number of scientists standing by to take your questions on social media. And also, if you visit the nasa.gov website, the full story, the full press release is on the top of nasa.gov right now. So thank you, everybody, for listening. Have a great day.
That concludes today's conference. Thank you for participating. You may disconnect at this time.